Okay, so working on the blackboard, let me introduce then the linear reservoir rainfall and off model. Yesterday I mentioned to you, I briefly introduced to you the time area model, and I suggested you to study independently, autonomously, the time area model. Now I would like to introduce together with you the linear reservoir. And those of you who already had a background in hydrology probably know both models, because these two models are the basis for rainfall and off modeling in hydrology. These were the first models that were conceived, both of them not really the first, because we can call the rational formula as a rainfall and off model. So the first model was the rational formula, and then these two models. And they are both linear. Linear means that the relationship between the river flow and the rainfall is linear. And basically, I think this is an important premise. What does it mean that a model is linear? Linear, from a technical point of view, means that you can apply the superimposition principle, which means that basically the following relationship applies. Fa plus b is equal to Fa plus Fb. This is one of the conditions for a relationship F to be linear. And the second one is that Fax is equal to A times Fx. These are the two necessary and sufficient conditions for a relationship F to be linear. This is the mathematical interpretation. The technical representation is that you can apply the superimposition principle. In our case, it means that the river flow that is given by a given rainfall can be obtained by summing to separate river flows given by two separate rainfall whose sum gives the total rainfall. So basically, if you have a rainfall of 10 and you obtain a given river flow for a rainfall of 10, you can obtain the same river flow by summing the two river flows that you get from a rainfall of 7 plus a rainfall of 3. So basically, in terms of river flows, I can say that Q, let me say, put it in this way. Q at time t given by a rainfall of 10 is equal to Q at time t given by a rainfall of 7 plus Q at time t given by a rainfall of 3. This is the superimposition principle in rainfall and off modeling, which, of course, in practice, it's not true. In practice, the rainfall and off relationship is not linear. And I say, of course, because it's clear that if you have two separate rainfall, their effect in terms of river flows is different with respect to the effect given by the sum of the two rainfalls. Because let's suppose that you get a river flow, a rainfall of 10, and then a sequence of dry days and another rainfall of 10. You may see that you may even not see any river flow, because if a rainfall of 10 falls on a dry soil, you don't see any river flow because the rainfall infiltrates. So two rainfall of 10 may produce no river flow if they are separated by a dry period. If you get a rainfall of 20, it means that the second 10, from 10 to 20, fall over a soil that is already wet, humid. And therefore, the effect in terms of river flow is more significant. There is a proverb, a saying, that says, it rains on the wet, meaning that it's an unfortunate situation. When it rains on the dry soil, it's a you know, it's a situation which is not concerning. If it rains over a saturated soil, a wet soil, it's an unfortunate situation because you may get a flood. So you understand that the same rainfall may produce different effects depending on the status of the system, which means that the relationship is not linear. Because if you have a linear relationship, then you have the same effect for a given input. Okay? So basically these are linear models, so they are, again, an approximation, which is not a problem, I mean, but we need to be aware of that. Okay, so when in hydrology we say that the model that we are using is linear, it's an important specification. And therefore it's important that you know what linear means. It means that you can apply the superimposition principle, or if you want to say it in mathematical terms, you have just to remember these two conditions. Just remember it, because this may be a question at the exam. Okay? So basically, as I said, these two models, the time area model and the linear reservoir, are the basis for hydrological modeling. They are linear. And I'm pretty sure that if you have a background in hydrology, as I said, you probably already know these models. But so this is one reason why I prefer that the time area model is studied independently. But for the linear reservoir, on the other hand, I prefer that we get back it, or let me say, study again it together, because I think it's interesting. It's interesting to know the basis. So if you already know the theory of the linear reservoir models, just forgive me, be patient, and follow me for about 15 minutes. So what is, how is the linear reservoir structured? The conceptual scheme, because this is a conceptual model, the conceptual scheme is obtained by assimilating the catchment to a tank, to a reservoir. So basically, we have a reservoir which contains a given volume of water, which I indicate with the symbol WT, because it's a time-varying quantity. And then we get rainfall inside this reservoir, let me call it RT. And then we assume that the discharge comes out from a bottom discharge from which we get the river flow QT. And this is the conceptual scheme that we would like to apply. And this conceptual scheme gives us the opportunity to formulate the relationships governing this rainfall runoff process. First of all, we know that the conservation of mass applies, so we can easily write down the conservation of mass for this reservoir. So let me write it down. And the conservation of mass basically says that the variation in time of WT is equal to RT minus QT. So maybe that in my slides I indicate the rainfall with the symbol P, because the Italian name for rainfall is pioggia, so in Italy we usually use PT to indicate rainfall. Just don't be concerned by the fact that the symbols may be different. So this is the mass balance equation for the reservoir. What's important to see here? It's extremely important to see that I introduced a state variable, W. This is important to notice because I needed to introduce this state variable to write down the mass balance equation, but of course this means that I have to add another relationship because I added one unknown. So at the beginning my unknown is Q. I added one more unknown, and therefore I need a second relationship. So you know that a second relationship can be an energy balance equation, but let me say that in this case the linear reservoirs assumes that the second relationship is empirical. And the second relationship is obtained by assuming that a linear dependence exists between Qt and W. This is reasonable because you can by intuition understand that the higher Wt, the higher the river discharge. If you have a higher volume of water stored in your catchment, you are expecting a higher river discharge in the river. So this is reasonable. What it's not really justified is the fact that the relationship is linear. Clearly it is non-linear. But we assume that the linear relationship applies. And this is very simply written as, let me write it in this way. Wt is equal to K multiplied Qt. This is a linear relationship. If K is constant, and you see that I didn't indicate any temporal dependence here, so if K is constant, then this is a linear relationship, which implies that K is as the dimension of a time. You see, Q is square length over time, W is a square length, so it means that K should have the dimension of a time. Remember it. And also, this relationship implies that K is a parameter. Do you remember that we define parameters as yeah, we used it alpha yesterday, but just don't, let's be flexible on the symbols, okay? Now today, because yesterday it was a different story, alpha, I used alpha to relate the river flow to rainfall. In this case, I'm relating the river flow to the storage. So for this reason, I prefer to use another symbol. Yes, but that's true that yesterday we called it alpha. Parameter is a quantity that appears in the equation which doesn't change the structure of the equation, so the equation is still linear, but of course it changes the specific shape. So basically, what do you note here? What can you see here? You see that for increasing K, you have an higher discharge at the outlet for a given volume. Okay. The opposite, sorry. For increasing K for a given volume, you have a lower discharge. Okay? Sorry. Perfect. Now, I said yesterday that it's important to see any physical meaning behind an empirical relationship. So, I said just a few minutes ago that I could use an energy balance equation here instead of an empirical equation. So now, let's look at this empirical equation and let's try to understand if I can see a physical meaning in it. What is this relationship? It's relating a bottom discharge from a reservoir to the storage. If you had some background in hydraulics, you may remember that there is a physical law called Torricelli's law that establishes the same relationship from a tank with an hole in the bottom. The Torricelli relationship allows us to compute the discharge from the hole depending on the water depth into the tank. It is the same thing here, because the storage is a volume that is of course proportional to the water depth into the tank. If you think of a tank, a real tank, of which you know the geometry, once that you know the water depth, you can compute the water volume stored in the tank. So let me now draw a second tank here, and this is a real tank, and let's indicate with HT, the water depth. And let's suppose that we have an hole in the bottom whose area is indicated by the symbol A. What does the Torricelli relationship say? The Torricelli relationship says that the Q from the hole So the discharge from the hole is given by the area of the hole times a reduction coefficient times the square root of 2gh, where g is gravity. This is what Torricelli's relationship, Torricelli's law says.
Can you please
Yes.
indicate Torricelli's?
This is Torricelli's law. And basically it says that if you have a real tank with water depth h into it and an hole whose area we indicate with A, you can compute the discharge from the hole. And the discharge is given by A, the area of the hole, times a reduction coefficient, which is very close to 1, times the square root of 2 times G times H. And let's not forget that H can be written as a function of W. And what is Torricelli's law? It's an energy balance equation. It's derived, we don't spend time to derive the Torricelli's law, but it's important to notice that it's just derived from the balance of energy. It's an energy balance. So, what can we conclude? We can conclude that our relationship linear here is very similar to Torricelli's law. It's very similar. It's simpler because it's linear. Torricelli's law is not linear. You see the square root. Torricelli's law is not linear. In this case, we adopted a linear relationship, which is very similar to the Torricelli's law. This means that basically we adopt an empirical relationship, which is an approximation of Torricelli's law. And therefore, our empirical relationship, it's an approximate energy balance equation. This is extremely important to notice. Whatever we have the opportunity to associate a physical meaning to an empirical relationship, we should always do that. Look, now we have two unknowns, Q and W. One parameter that we can assume to be known for now. And therefore we have two unknowns, two equations. We can solve it. It's a system that includes a partial differential equation, and therefore we already see the need for computing an integral in some way. If we want to compute Q, we need an integral here, because there is a differential term in these two equations, unfortunately or fortunately. So we already see the need for computing an integral. And then we understand that we may need to compute it numerically or analytically, we will see. Okay, questions on this, and then I compute the integral. And then we are done. Okay, first, before I move forward, look, we could already be able, once somebody gave to me the rainfall, and once somebody gave to me the value for K, we could be already able to apply this model through a numerical solution. By approximating dW with a finite difference increment, we are already able now to use our model. So I could turn to the PC now and apply this model in practice. But given that there is the possibility to move a bit forward with an analytical integration, I want to show you how it works. Okay? Perfect. Now let me integrate this equation, and And first of all, we may notice that we can reduce the number of the two equations to 1 by eliminating an unknown, because we can substitute in the first equation, we can substitute either W or Q with the value, the corresponding value that we can get from the second equation. So we can operate a substitution, eliminate one variable, and reduce to one equation. So we certainly have to do that. And when you move forward with such an operation, such a procedure, so when you are eliminating a variable to reduce the number of equations, this is perfectly fine, but you have to take care not to eliminate the variable that you are interested in. So basically, if I substituted here the value of Q here, it wouldn't be a wise choice because, you know, I'm interested in Q. It's better to substitute W because I'm not directly interested in W. So now let me take W from the second equation and substitute it in the first equation, which means that W will disappear from the equations. And then I can write it in this way. Not sure you can see here. So instead of W, KQ T divided by the T is equal to RT minus QT. This is the equation, the differential equation that we have to solve. Now I'm cleaning this part of the blackboard and I'm keeping just the relationship that we have to integrate on the left-hand side. Okay. So, now let me divide everything by k here. I can do that because k is a constant, so I can bring it out from the derivative. So I can write, and let me also separate the variables. I can write that dq t over dt plus 1 over k qt is equal to 1 over k RT. You see that I separated the variable. I put all the q's on the left-hand side, and I isolated R on the right-hand side. Good. Now, let me use an artificial resolution by multiplying every term on the left and right hand sides times e to the power of t over k. Let me write it. So e to the power of t over k that multiplies the derivative of qt against time plus e to the power of t over k that multiplies 1 over k qt is equal to 1 over k RT times e to the power of t over k. I mean, I can do that because for a given time e to the power of t over k is an assigned value. So I can multiply first and second term for this quantity. We are working in differential terms now, so time is assigned. Every time that we compute this equation, time is assigned, and therefore e to the power of t over k is a constant. Or you can see it in another way, which physically is more reasonable. What is our purpose? Is to compute q at a given time t. So given. It means that t is given. So e to the power of t over k is a constant. Once that the time is given. is this quantity at the left-hand side. This is the derivative of the time of q times e to the power of t over k. Try it. If you compute this derivative, you get what stands here. And let me just try to explain it. This is the derivative of a product. Sorry, I forgot qt. This is the derivative of a product. And therefore, you can obtain it by computing the derivative of the first term, which is dqt over dt, times the second term unchanged, e to the power of t over k, plus the derivative of the second term, which is e to the power of t over k, and the derivative doesn't change, but you have to multiply for the derivative of the exponent, which is 1 over k. And then multiply it again for the first term, not unchanged, which is qt. Is not clear? It's clear, okay, thank you. Okay, perfect. So at this stage, I can compute my integral. And so what does it mean computing the integral? It means that these differential terms, I am summing them starting from a given time, let me call it time 0, up to time t, because you know these are increments of q, which I need to sum, starting from initial time to the given time t. So let me compute. Let me compute the second term first. Integral from 0 to t of 1 over k rt times e to the power of t over k in the t. But let me call it tau, okay? Every t here should be substituted by a tau. Because, why? Because t is the time at which I want to compute my river flow, and I need to get to t by infinitesimal increments. And I cannot call them dt, because it would mean that I am changing the t value. I need to use another symbol for the increments, which is the tau. Is it clear? Okay. It's also called in Italian the variabile di integrazione, which means I don't know how to say in English. It's probably the variable of integration. This is a literal translation. I'm not sure it's, but it is a common practice when integrating analytically to use a different symbol for the variables that is summed up in the integral. Okay. And then there is the first term. The first term is easier to integrate because simply if you take the integral, you eliminate the derivative. But it needs to be computed. Qt e to the power of t over k. It needs to be computed between the extremes 0 and t. Basically, we already have the result of the integral, but it needs to be computed between the extremes, the given extremes. Okay, so we are almost done. Now let me compute the right-hand side at the two extremes. So basically, if we compute it at the extreme t, I keep the same term unchanged, so I can write it down in this way: qt times e to the power of t over k minus, now I have to compute at the time 0. And basically time 0 I get q0, and e to the power of 0 is 1, so it's just minus q0. And then I have my integral here. And let me just copy it unchanged. But let me just put it in this way. 1 over k e to the power of tau over k times r tau tau. Any doubt? Yeah, please.
Why we did use a tau
in the integral?
Yeah, in the left-hand side, because we are using the.
Okay. Let's say that. Let's qt and t. So let's suppose that the time t at which I want to compute the integral is this one, okay? And let's suppose that this is time 0. Let's suppose that this is q0. So you start from q0 and you have an hydrograph that goes up, let's say, to t. And this is qt. Basically, the way in which you compute it is by adding increments at infinitesimal time step. In this case, they are depicted as finite time step, but think as they were infinitely, very small, okay? And then you compute at any time the dq. So your integral basically computes at any time the dq, and the dq which is here. It's like a summation, and you move forward through time steps that you need a symbol for them. You can't say dt, because t is fixed. You have to use another symbol. And therefore I used the tau. Because when I compute the integral, you know, of a quantity that it's an infinitesimal increment for a given time, I'm not changing the given time inside the integral. I'm just using time steps to get to this value of time, which is given. So I can't say dt. It's a mistake. It's a mistake that many times we do, because when we compute an integral of an infinitesimal part, many times, let's say that you have to compute something which is at the x. So basically, when you compute the integral, you have to change the symbol, the integral of the tau, not the same the x, because this becomes generic and variable while x is fixed. In our case, t is fixed. When you compute the integral, then you start from 0 to get to t, and the time step becomes generic. You have to use a different symbol. And I'm sorry, this is something that is part of the analytical theory. Maybe that I'm not very good in explaining this, because this is a mathematical detail. But it's when you compute an integral, it is usual practice that you have to change the symbol.
I'm sorry, but my question was, we have changed the symbol on the right-hand side, but not on the left-hand side.
Yes, of course, because you know, on the right-hand side we are computing we are computing an integral. On the left-hand side, we don't need to compute an integral. We just eliminated the derivative.
Okay.
Okay, but you know, we use the same. Yeah, you are right anyway. You are right, because if I keep it in this way, of course, it's not clear that you need to use, it's not correct to use the same symbol. You are right, okay, let's put it here, tau, okay? I think you are right. Sorry for that, now I understood your question. Because tau should assume the value of t and 0, alternatively. So you're right, one should change it. It doesn't change the result, because here I used already, okay? Perfect. Okay, now we can move forward, and what I would like to do, given that I am interested in getting the value of qt, I would like to divide any term by e to the power of t over k. So basically I can write that qt, which is what I want to obtain, is equal to, I move to the right hand side, integral between 0 and t of 1 over k e to the power of tau over k divided by e to the power of t over k. E to the power of t over k, again, it's a constant. I can bring it inside the integral. And then I have r tau, d tau, plus q0 times e to the power of minus t over k. You can already see that the river flow is given by two terms. One is given to rainfall, it's the integral. The second term is a depletion term. It's a Q0 that slowly goes to 0. It's a depletion term. You see that for increasing t, this term vanishes.
Is that minus?
Minus here, because it's divided. Okay? Perfect. And now we are done. Let me just write this integral in a more compact way. And so I clean here. So I can write qt is equal to the integral between 0 and t of 1 over k e to the power of minus t minus tau over k rt d tau plus q0 e to the power of minus t over k. That's it.